So today I will present the work I've been doing for my thesis. And before I begin, just quickly, I'm going to finish my PhD in January, and it will be nice to have a job afterwards. So if, in case anyone knows of any postdoc position, please let me know. Okay, let's begin. So, okay, yeah. So these are the brief contents of my presentation. I'll first give a brief introduction about the formation of supermassive black hole, and then I will talk about the theory which we are using, and then I'll talk about the cosmological simulation through which I'm implementing that theory, Pinocchio, and then I will talk about the results I get, and finally, the gravitational wave background, which is generated by those black holes. So let's start with the introduction. Now, as most of us in the room already know, that we have quite a good understanding of how stellar mass black holes form, but the same cannot be said for supermassive black holes. There are many theories, each have their own pros and cons. So there is no unanimous agreement on which theory should work the best. And what exactly are these black holes? These are the black holes defined to be more massive than around 10 to the 5 solar masses, and they are found to be present in most large galaxies, and now we also have images of them. So the main problem comes from the fact that we have observed high redshift quasars, which are believed to be powered by black holes more massive than a billion solar masses. And if you have to think how they would have formed, if they started from a stellar mass seed or somewhere close to that at early universe, there is just not enough time for them to grow this much through just accretion or mergers. So to better understand that, we can take a look at the plot from Wang et al., and in which they show some of the quasars, high redshift quasars, quite massive ones, which were found. And all the tracks, they refer to their mass growth if it is assumed that they are growing via Eddington accretion. And basically, this plot tells us like what should have been the initial mass of the seeds according to the redshift where they were initially seeded. So and also these bands, they refer to different seeding mechanisms. The first is the direct collapse black hole method, which is the most popular, in which an entire cloud collapses to form a single supermassive star or directly a black hole. It predicts black holes, the initial seed black holes to be around from 10 to the 4 to 10 to the 6 solar masses. Then we have the dense star cluster, in which there are runaway mergers. They predict slightly lower seed masses, and then the remnants of population C star, which depict even lower. So let's say if all of these black holes, if they were initially seeded at 30 redshift, then their masses have to be quite high, and all of these, and they will lie between different ranges of different seeding mechanism. If the mass is around 10 to the 4, then it should be around the direct collapse black hole range, and then it has to grow with Eddington accretion in order to reach the mass which we observe. So the problem is we are not sure if these black holes can accrete for Eddington accretion for the entire lifetime. So we cannot just always assume that this curve is going to be true. So the best case scenario would be to have even more massive seeds in the early universe. So let's say if seeds are forming at redshift 30, then if we have the initial mass at 10 to the 5, then if they are growing, they don't necessarily need to be Eddington accretion for most of their lifetime in order to explain those black holes. And all of these methods have, as I said, pros and cons. And today I will talk about a different kind of population 3 mechanism, which can predict more massive seeds. So basically what I'm talking about is population 3.1 star as the seeds of these supermassive black holes. What are these stars exactly? These are the normal population 3, which are found via primordial gas composition in the early universe, in the dark matter mini halos at high redshift. But the point one comes from the fact that we are assuming that these population 3 stars, when they are forming in a dark matter mini halo, they are isolated from all the other sources. So they are inside an isolation bubble, so that they are not affected by the feedback from any other kind of source. This allows the stars to grow even more massive with lesser fragmentation. So just a pictorial representation of it. So if we have a pristine environment at high redshift in a dark matter mini halo, there are no other sources nearby. So the star which is forming at the center will be a population 3.1 by definition. Now, once it has formed, it will have a feedback bubble around it. It will exert some feedback. And then if there is another star starts to form nearby, if it's inside this feedback sphere, it is going to be affected. Its accretion is going to be affected. So we will call it population 3.2. It can even be a POP2 star depending if it has been chemically polluted or not. So this is going to be POP 3.2. Now let's say there is another star forming right outside of the sphere of the first and even the second, or conversely, if this star is isolated from, or in this sphere, there are no other sources when this star was forming, this would also be a population 3.1 star. So in this theory, this feedback, this sphere is called the isolation distance, and this is right now a free parameter which does have some physical significance, but right now we can treat it as a free parameter. So depending on this isolation distance, you can have different number of black holes, which are different number of seeded halos, and then eventually black holes, which I'll talk about later. So via this mechanism, since there are no less sources of feedback, these stars can grow massive up to 10. It has been shown up to 10 to the 3 solar masses, but we would like to do even better. And one way to do better is to consider that to take advantage of the fact that these stars are forming inside dark matter mini halos. And if we assume the dark matter particles to be WIMPs, and if they are doing self-annihilation inside the star, then this energy released by the annihilation can be captured by the star. And this can allow the star to swell. It can remain relatively cool. This can reduce the ionizing feedback, and then it can keep on accreting more and more matter, and the fragmentation is also reduced. So in theory, it can keep on accreting almost the entire content of the mini halo, entire baryonic content of the mini halo, and reach up to 10 to the 5 before it collapses and forms a supermassive black hole of 10 to the 5. And this is happening at quite early, at high redshifts. And then if these black holes start by 10 to the 5 solar mass, then there's no need to invoke Eddington accretion throughout the entire history. So my work is to implement this seeding mechanism on a cosmological box using the help of Pinocchio, not the character, but just the code. And it's not an n-body code. It's a semi-analytical code which uses Lagrangian perturbation theory to evolve over densities in a large cosmological box. And it's a very fast code, and it can output the catalogs of all the halos at different redshift. It provides information such as the mass, the position, the velocity, and it also gives a histories file. It basically tells the merger histories of every single halo and with which halo it merged to and the exact redshift at which it merged. So combining this information, I can scan all the halos which are appearing in a box. We used a 60 megaparsec box, and I try to find how many of these halos, when they are appearing, were isolated from other halos with the isolation distance as a free parameter. So I'll show the results, the finding. So here I show the number density of seeded halos, which as a function of redshift and as a function of the free parameter isolation distance. It's in proper units, the isolation distance, but the number density is in co-moving units. And a striking feature of the model is that most of the seeds are already in place by redshift around 25. The black point here, this represents an estimate based on the observed number density of black holes in the local universe, of supermassive black holes. And we can say that for a certain range of our isolation parameter, around 100, this model can explain. The dip in the front is because of mergers of seeded halos, or by extension, mergers of the supermassive black holes. And if we want to compare it to some other kind of seeding mechanism or different kind of mechanism to form black holes, here I show one which is the halo mass threshold, which is something which is usually used in simulations such as Illustris, in which every halo more massive than, for example, 7 to the 10 times 10 solar mass is seeded with a black hole, and we can see that the number density rises quite sharply. It is dependent on the resolution, but still we can see that the difference is going to be there. We can also take a look at direct collapse method, and the conditions for direct collapse method for black holes to form via direct collapse are not that common in the early universe. So the number density is quite different at very high redshift. So this gives us interesting scenario to test different mechanisms by looking at the number density or by counting the number of black holes in the early universe using the surveys we have now. Then we can, with all the surveys coming up, we can actually start putting some more observational data points on these kind of plots. And from recent results from Harikane, in which they had, I think, around 10 to 12 AGNs at high redshift, they were able to give some estimates on the lower limit of number density at high redshift. And these limits are only going to get better as we have more and more results. So this is promising. And we can also take a look at the clustering of these seeded halos. Since I have the position of all the halos in the box, I can compute the 3D 2-point correlation function. And here I show it for cases of 50 kiloparsec and 100 kiloparsec, the isolation distance. And I'm showing it for 4 sets of halos. The blue one's the seeded halo only, the orange all halos, the green the HMT one, which I showed, which is based on the illustrious kind of seeding mechanism, and the red is the control sample, which basically is that I randomly select halos from the pool of all the halos with the same mass and number distribution as the seeded halos. So this can give us a direct comparison with the random set of halos with the seeded halos. And we can see that the clustering of these seeded halos is always lower. Another thing I should mention is that we are only concerned with scales in this plot, scales greater than 2 or 3 megaparsec. This is at redshift 0, because Pinocchio is a dark matter only code and it does not resolve substructures inside a halo. So we are only concerned with scales greater than the scale of 1 halo. So in the 50 kiloparsec case, the signal is not that strong, but for 100 kiloparsec, the clustering is definitely lower. And this can give us another interesting way to test different kind of theories for the formation of these black holes. And we can also talk about the evolution of clustering. And here I show the projected correlation function on the plane of sky for 50 kiloparsec the top row and 100 kiloparsec in the bottom row. And again, the blue lines correspond to the seeded halos at that redshift, and the red is a control sample, the same with the same mass and number distribution as the seeded halos at that redshift. And the vertical gray bands which you see, they correspond to the size of the isolation sphere when most of these halos were being seeded at redshifts of 30 something. So we can see that as I showed in the previous plot, the clustering is definite of the seeded halos are definitely lower for all the cases, but we can see a significant drop in the clustering below the scale of this isolation sphere, which is expected because you expect less number of seeded less number of halos to be separated via separations less than the isolation sphere, because we are effectively clearing. They are like effectively feedback cleared bubbles which are forming. And this signal still remains up to redshifts of 2 and 3 before it fades. And once again, this can give us another opportunity to test these kind of models while looking at clustering at higher redshift. And in order to do good clustering analysis at high redshift, we need a lot of AGNs or the sources, and hopefully in the future it should be possible. Finally, I can also talk a bit about the gravitation wave background. How much time do I have? Plenty. Okay, perfect. Thank you. So we all recently heard about the announcement just a little over a month ago from Nanograph and the international collaboration for pulsar timing arrays, in which they were able to detect gravitation wave. They claim that there is a signal which could be due to the gravitational wave background due to the mergers of supermassive black holes, and the frequencies which they are aiming are around the nanohertz. And this is just a representation of the 65 millipulsars Nanograph used to calculate the background. And since I am also dealing with supermassive black holes, I can try to make some predictions from this kind of model. So in order to do that, I can look at the number of mergers which are happening between all of the seeded halos. And we have a few mergers. For 50 kiloparsec, we have like 3,000 mergers happening in our 60 megaparsec box. For 100 kiloparsec, which had number densities closer to the observed number density, the number of mergers are around 200, a bit low, but we'll see how it turns out. So I have the number, I have the halo, I know which are the halos which are merging. I can create a merger event rate, and from that I can calculate the background. But as I said before that, Pinocchio, the code I'm using, it's a dark matter only code. I don't have actual black holes in the halos. I'm just tagging the halos to be seeded. So in order to calculate the background, I need the mass. It's fundamental. I need the mass of the black holes and the redshift where these black holes are merging. So since I only have dark matter halos and I know the mass of the halos, I can turn to scaling relations which relate the mass of the black holes with the mass of the dark matter halo. And I just put a floor here at 10 to the 5 because we are assuming the minimum mass to be 10 to the 5. And here I show different scaling relations. The Matteo, this is from simulations. Motley-Parkdale, I think this is from observations. And a simple power law, which is a toy model in which black holes grow via power law, starting from 10 to the 5 solar mass in halos of 10 to the 6, and they grow. Then there is another model which is being prepared in our group, led by Vieri Camelli, in which he is seeding these dark matter halos with actual galaxy by using semi-analytical codes, Gaia. And these are the results he gave me some time ago, and we are working on an accretion mode. So we will have better results hopefully soon. So I can take these models, take the mass of the halo, get the mass of the black hole out of it, then apply the scaling relation with some dispersion on them, and then I can calculate the background. So here I show the background at the strain of the background at frequency of 1 near inverse. And this gray band refers to the value measured by nanograph recently. I'm showing it for 3 cases of the isolation distance. And we can see that this model can reach this kind of level, although it's a bit high, or rather the values are a bit low. But again, this is still in a very preliminary stage. It depends heavily on the mass relation you are using, the dispersion you are using, and the time you assume for the black holes to merge. So this is still a work in progress, but again, the results are promising, and we're still actively working on it. And this brings me to my conclusions. So I showed how population 3.1 stars can grow up to 10 to the 5, and they can be the seeds of the supermassive black hole if we assume an isolation distance, and which is a free parameter. And I showed that for certain values of this parameter, we can explain the number density of these black holes in the local universe. And I showed that also about the clustering signal, which could be an interesting scenario to probe these kind of mechanisms. And finally, I showed about the gravitational wave background, that we can also start making predictions for the background, although there are a lot of uncertainties right now, but it will only improve from here. And finally, the future work, as I mentioned, that my colleague is developing a better relation between the mass of the black hole and the halo, and a more physically motivated relation. So we'll implement them and have more improved prediction for the background.